Hi everyone, in this video I'm going to introduce the first set of notes for Unit 8 in Chem and Section 8.1 looks at molarity and solutions. I'm going to be posting the unit objectives, which look like this in the Unit 8 topic in Classroom, and you can see here's the part of the textbook that corresponds to this topic, and here's some of the objectives we're going to be talking about. So a little bit of vocabulary and some simple calculations are going to be introduced here. I'm going to start by reminding you about a flowchart we looked at back in, it was probably September. And I said all matter can be classified as either a pure substance or a mixture. And we're going to be focusing on this part of the chart down here. Mixtures can either be homogeneous or heterogeneous. And a homogeneous mixture is synonymous with a solution. Most of the time we're going to be talking about solutions of a solid dissolved in a liquid or a liquid dissolved in a liquid. But really, there's lots of different types of solution. Even brass is a solution of a solid dissolved in a solid technically, and fog is a solution of a liquid dissolved in a gas. So the word solution simply means a homogeneous mixture, something that is evenly mixed and contains more than one substance. We're going to focus on solutions made from a solute and a solvent. So this is the first important bit of vocabulary that I want to introduce. The solute is the substance that's in smaller quantity, and it's often a solid, and the solvent is the substance that's in larger quantity, and that's very often water. So most of the time we're going to be talking about solid solutes dissolved in some large quantity of water. For instance, a saline solution, like you might use for contact lenses, is a solution where the salt is the solute and the solvent is water. So those are important terms. Solute, solvent, and solution. The solute is the substance being dissolved, or the solvent is the substance that's doing the dissolving, so to speak, and the solution is the resulting mixture. An example, again, would be saline solution or salt water. So that's an example that's a good one to start with. So there's a few other bits of vocabulary that I want to introduce here before we get into the calculations. First of all, the one on the left there is more concentrated and the one on the right is more dilute. So concentrated and dilute is how we're going to describe solutions which have more solute or less solute present relatively. And the word aqueous is another one we talked about a little bit earlier. An aqueous solution is simply any solution in which the solvent is water. So we introduced this and we talked about state symbols, S for solid, L for liquid, G for gas, as subscripts in a chemical equation. And AQ indicates that the reactant or product is dissolved in water in aqueous solution. Sometimes pronounced aqueous or aqueous, but that's an important term. So here is the rundown of all the vocabulary, the terminology so far, guys. Solution, solute, and solvent. Make sure you get the solute, you don't get the solute and solvent mixed up. I guess the word solvent has more letters in it than the word solute, so that might be an easy way to remember that the solute is the substance in smaller quantity. Other terminology, concentrated and dilute. And we'll talk about whether substances are soluble versus relatively insoluble. So, for instance, chalk doesn't really dissolve well in water, but table salt does. The last term in this list is the term stock. So a stock solution is simply something that's routinely used and is prepared in concentrated form. So sometimes if we want to use a particular concentration of solution, we will dilute it from a more concentrated stock solution. So that's a term that I wanted to introduce now as well. So whether a solution is concentrated or dilute is going to be quantified with a quantity called molarity. And the molarity of a solution is defined as moles of solute per liters of solution. This is an important formula and concept we're going to spend a lot of time talking about, and it's the beginning of some of the quantitative part of this unit. You might remember that a lot of solutions that we used were labeled as being, for instance, 3 molar or 2 molar. This is how we would read a quantity like this. 6 molar hydrochloric acid is 6 moles of hydrochloric acid per liter of aqueous solution, or per liter of solution total. 9 molar hydrochloric acid is more common. So let's talk about how this equation can be used. You'll see that I've rearranged the equation 3 different ways, solving for M, solving for V, solving for N. And I want to define each of those terms first. The uppercase letter M is not only the symbol for the quantity molarity, but it's also the symbol for the units molarity. The term N is the quantity number of moles, and of course the units are moles. And the quantity volume is given by an uppercase letter V, and the volume must be in liters. Notice that all volumes need to be in liters, not in milliliters, which is a really common mistake since most of the time in the lab we measure a volume in milliliters, but we need to convert to liters before we use any of these formulas. That's because molarity is defined as moles per liter. So again, the uppercase letter M is used for the quantity molarity, but is also understood to be notation for the units moles per liter, uppercase letter M, molarity. So let's try out a calculation or two using this formula. When we're doing calculations using molarity, we need to make sure that the solute amount is in moles and the volume is in liters. I'm going to jump to the document camera where I've got this particular problem printed out so I can show you how I'd write the solution to this. It says a solution with a volume of 480 milliliters contains 2 moles of potassium hydroxide. So first of all, I identify the volume is given to me. Notice it's given to me in milliliters. I'm going to go ahead and convert that to liters right away. I've kept 3 significant figures there because I was given 3 significant figures to begin with. 480 mils is 0.48 liters. And I'm also given a mole amount. The number of moles here is 2, and that's also the 2 significant figures. And now I can solve for molarity. Molarity is number of moles divided by volume. And if I do that calculation, I'll get the molarity. Notice that the units that I'm given are moles per liter. That's known as molarity, right? So that's going to be 2 moles divided by 0.48 liters. That gives me a molarity of 4.166 repeating. So I'm going to round that to 3 significant figures, and that gives me 4.17 molar. So let's take a look at a second example. This is also in the PowerPoint that is posted online. But you can pause the video right now. It'd probably be best to try this problem on your own first. And then when you're ready to see the solution, go ahead and unpause the video. The first thing I'm hoping people caught is that the amount of solute here is given in grams, not in moles. So in order to calculate N, the number of moles of solute, we're going to have to do a gram-mole conversion. So I'm going to do that right here by writing the number of moles is going to be given by taking the 14 grams of sodium hydroxide indicated and converting to moles, right? We want to get rid of grams of sodium hydroxide. We want to end up with moles. And we're going to have now an actual number of moles of solute. And in this formula, N has to be in moles and V has to be in liters. The molar mass of sodium hydroxide is 40. And you use a different periodic table, you might get a slightly different number there, but you know if we use the purple ones, we're going to agree within at least 1,000th of a gram per mole. So I'm going to do that calculation and see how many moles I'm actually talking about. 14 grams of sodium hydroxide is 0.35 moles. Now, the volume needs to be in liters, and here it's given in milliliters, so remember that 500 milliliters is half a liter, and that volume again was given to 3 significant figures. I'm going to keep the number of significant figures in my conversion. I've kept 3 significant figures, there we go, in my number of moles, and so when I calculate molarity as M equals N over V, then molarity is going to be calculated. Remember the units are moles per liter, also known as molar, as 0.35 divided by 0.5. So this is a 0.7 molar solution, and again, I've used 3 significant figures there. Let's try one more. Here's a third example problem, and again, might be a good idea to pause the video, try it on your own, and then unpause to see how you did. In this calculation, it's asking how many grams are required to prepare 400 mils of 3 molar solution. we're solving for an amount of solute, which is indicated by the letter N here. But notice we're going to have to first of all solve for number of moles, and then we're going to need to convert it to grams. The molarity is given as 3 molar, only 2 significant figures there, and the volume is given as 400 milliliters. I'm going to go ahead and convert that to liters right now. And the way we solve for number of moles is N equals mV. That's 3 multiplied by 0.4. That means 1.2 moles. And I've only got 2 significant figures according to this molarity. In order to answer the question, though, I'm going to have to take 1.2 moles, and we're talking about sodium hydroxide again, and convert it to grams. Sodium hydroxide is 40 grams per mole, and so I end up with number of moles of sodium hydroxide that was in the solution, right? And that is 1.2 multiplied by 40, and I get 48 grams of sodium hydroxide in the solution. So this gram-mole conversion is sometimes necessary. Sometimes, if we want to figure out how many grams of solute are actually present, the conversion from moles to grams has to happen. Alternatively, if we're given a number of grams, we need to convert it to moles before we can calculate molarity. Let's try one more example problem. Here's the fourth one, which is in the PowerPoint, and it says a glucose solution with a volume of 2 liters. So I'm going to go ahead and start the shopping list here. Volume is 2 liters, and it contains 72 grams of glucose. Well, that is an amount of solute, but it's given in grams. So I'm going to go ahead and convert it to moles right away, and I'm just going to use a cursive letter G to indicate glucose, because that's easier to write than the formula for glucose. And here, the molar mass is given as 180 grams per mole. So how many moles am I actually talking about here? We'll need to calculate that before we can proceed. 72 divided by 180 gives me 0.4 moles of solute. Now the molarity, of course, is given by N divided by V, the number of moles divided by the liters of solution is going to give me a molarity. Here, I can report this to 2 significant figures. So there's a couple of good examples of molarity calculations. We'll be practicing this in an upcoming assignment, which I'm going to post in Classroom soon.